Heterogeneity is the miracle of difference. It's a miracle because when you think about how evolution acts on us, it tends to make all of us the same. If there's one best way to behave or one best way to be, then over time, the people who are best are going to be the ones that survive so that we all end up looking alike. And so the fact that we exhibit differences in our behavior and in our emotions and even in our genes, this is a result of the fact that we have different environments. And so you might live in an area, for example, that requires you to be able to get together with your friends to hunt for food. If that's the case, then having lots of friends is going to be very important. And if you're raised in an environment where you don't want to be in contact with people who have deadly diseases, it might be really important for you not to have very many friends. And this is exactly the same kind of variation that we study when we study social networks, because we find that genetic variation can actually help to explain these behavioral variations that we see in the real world.
We're all used to thinking about averages. If we look at people and get the average height, that gives us a good ability to understand how people are and what we should expect in the next person that comes along. Lots of things in the world work that way, and averages are good ways of thinking about them. But lots of things don't work that way. So if you look at say, websites on the internet and look at how many links a particular website has, you find that there is no well-defined average, or the average is just a kind of a useless concept. There's such huge fluctuations, with some websites having hundreds of millions of links to them, other websites having only one or two. In fact, many have only a couple links to them. That the average number of links just gives you no good information about how the web is linked together. Same thing is true in epidemiology. When you look at the number of people to whom one person is potentially linked, say, in spreading a virus. There's huge differences, and you really need to take those huge differences into account if you're going to understand these kinds of systems.
Well, disorder and heterogeneity is the richness of the system, is what allows us to have things which are not flat, which are not boring. A tank full of gas would be somehow a complex system, but it's not like that just because, the individual molecules are all the same. What we look into complex system is diversity, is the fact that we have agents with different behaviors. And this create a richness of dynamical processes and cooperative phenomena that is what is the interesting part of complex systems.
And we looked at collective problem solving in groups. And we did simulations where the various agents were looking at each other, but then they were also playing around and experimenting. And the question was, how did the interplay between their strategies in terms of where to look around and in terms of experimenting and talking to each other affect systemic performance? And one of the surprises to me was that even given a system that was seemingly mostly deterministic, that given the same starting point, that there really was quite a major variation in the outcomes in the system.
Heterogeneity is a very important element in biological and social systems, while it's not so pronounced in physical systems. That's why biological and social systems are so much more difficult to understand. However, it's not only a matter of difficulty. Heterogeneity also has a functional aspect, because in many systems, heterogeneity creates a higher level of robustness.
I think heterogeneity in the system we are interested in play an enormous role. And it is something that is currently, in my opinion, not, let's say, seen from other disciplines, like, let's say, mainstream economics. Because, you have some needs, then the needs are the needs of describing a rational agent, and this is, of course, necessary to start with a scientific description. But this is quite far from reality, because in reality you have agents which might be rational, but they might be of size, of interest, of time scales, completely different. And this is a huge challenge for science. And we have seen this experimentally by investigating how institutions, how individuals, how companies act in a market, and they act in a specialized and different way.
Well, again, the individual languages, if you look in detail, that each person actually has their own language, which in some ways is very different from that of others. And the reason is that each of us has a different history of interactions with the world, with the environment. We all have different concerns that are the source of meanings in our interactions with others. We are in a particular spatial location where different languages are being spoken. So if you study language, you see actually that it's incredibly heterogeneous, even though it looks like it is coherent, but actually the heterogeneity is very important. And as a consequence, language is always changing because new influences are coming, or subpopulations are becoming more important, or new situations are arising. So language is really a living system that's continuously evolving, due to this heterogeneity.
The naive view of a system is that it's homogeneous. That means if you're a little microscopic Maxwell demon swimming around in a glass of water, everything looks the same at all times. But it's exactly the opposite of this. If you are on the size of a molecule swimming around in a glass of water, you would see regions where the water is ordered in one fashion and regions where the water is ordered in a different fashion. That's what heterogeneity means. Instead of being homogeneous, a glass of water is extremely heterogeneous. And it's these heterogeneities that we study in collaboration between Boston University and the University of Barcelona in the group led by Giancarlo Francesi. This study has led to a deeper understanding of what is special about water.
Yeah, heterogeneity can arise from different sources. It can come from within the system. So like in the case of the self-organized patterns or self-organized fluctuations. But most systems also are exposed to heterogeneous environment. And actually, when you have a heterogeneity in the environment, in general, it tends somehow to smooth out most of the cycles, dynamics that you expect to be self-organized in the systems. On the other hand, sometimes heterogeneity can actually be amplified by the system. For instance, if a system tends to have a cycle or produce chaos, but it just doesn't do it by itself. If you push it a little bit by some fluctuations in the environment, it may be boosted. So the interaction between external heterogeneity, spatial or temporal, and what happens within the system makes things really complex indeed.
Heterogeneity means that the components of the system one is studying are not all the same. Sometimes for simplistic reasons and because there is nothing you can do in terms of analysis, we assume that basically everything is the same. We can think of a population of people or animals or entities as being all the same. And so we can ascribe to them some properties like, the stock market went up today. In that sentence, essentially, we assume that all stocks behave the same way. They all went up. But if we look a little bit carefully, of course, even when the stock market goes up one day, some stocks went down, some other stocks didn't do anything, and some stocks actually went up. So heterogeneity means essentially taking into account and respecting in an extremely careful way the fact that entities are different from each other when they are part of a very large system. Now that's at the level of populations. In dynamics, we see the same thing. We see systems that evolve in time, but not all the parts of the system are evolving the same way.
Heterogeneity is hugely important in complex systems, and one example is the huge difference in the number of links different nodes have on the World Wide Web or on the cell. Some web pages on the World Wide Web, like Google, has hundreds of millions of links pointing to them. Others, like my web page, has a dozen or none, as a matter of fact. In the same way, in the cell, some of the chemicals interact with hundreds of other chemicals. Others interact with only one or two. one of the story of the last decade of complex systems was to understand the origin of these heterogeneities. And in some cases we do actually, and we have very precise theory to describe them. And we also understand how important they are. Because if there's huge differences between the nodes, it makes a very important difference whether you knock out, for example, a hub or you knock out a small node from the network. So this heterogeneity has a very, very strong impact on the system's ability to function and the system's ability to withstand errors and failures.
Heterogeneity plays a major role, and to understand that, we have to move on from the domain of equilibrium systems to fully embrace this non-equilibrium situation in which biology takes place. For example, in equilibrium systems, if we deposit a drop of ink into a glass of water, we'll see how this situation is going to be homogenized through time. That is to say, we'll end up with a situation in which all water looks pretty much the same. Thus, it was very difficult to understand biology from that perspective. And the reason is not that biology defeats physics, but we have to change our paradigm. We have to consider non-equilibrium systems. And that under that situation, we can fully embrace this process by which fluctuations now play a major role. There's symmetry breaking, and these small fluctuations play a major role in the sense of canalizing the system towards one direction or another one, both in time and space.